All right, so in this penultimate video, we're going to talk about a final set of concentrations or concentration units, and then just do a couple quick calculations. And so our final concentration unit, and I should say units, since I have two on this list, are called the mole fraction and the mole percent. And so here, what we're going to be looking at is doing a concentration unit that worries about, instead of grams, as we did with our mass percents, moles of solute divided by the total number of moles, where that total number of moles is constituted of the moles of any solute or solutes you have in solution, plus the moles of solvent. So in the numerator, we have moles of solute, and the denominator, we have the total amount of moles. So moles of solute, and I'll put a little caret here to say moles of solutes, if that's pertinent, plus the moles of solvent, everything added together. And our unit here is this chi, this X from the Greek alphabet, and then we just put solute in subscript to say whatever we're talking about. So if we're talking about the mole fraction, and so far we're just doing the mole fraction. The mole fraction of O2 is the moles of O2 divided by the total number of moles of whatever we're talking about. And, this gets widely used when we're talking about solutions with a couple of different solutes that can vary widely depending on how they're prepared. And so if we look at the compounds that make up, the air that we breathe every day, or compounds in air, and you could also say components of air, by mole fraction, we would say that the mole fraction of N2 is 3/4, or, meaning that 3/4 of the air that we breathe is nitrogen gas. We'd say the mole fraction of O2, the amount of moles of oxygen per total moles, is 1/5. The mole fraction of argon is 1/100. And the mole fraction of CO2 is 1/2500. And, if we don't want to choose to represent our amount of these different gases in terms of fraction, as we've done here with this is mole fraction right here, we could also represent them as a percentage, where we just take the mole fraction, multiply it by 100, and so we can say that the mole fraction of N2 is 3/4, and the mole percent is 75%. And that's probably a figure you've seen a lot online. So now what we're going to do is we're going to do two different questions that just ask us to calculate the concentration of something in terms of many of the different concentration units that we've talked about so far. And in this case, I'm going to once again ask you to pause the video, and you might find it most helpful to, pause the video, solve all of these for yourself, and then just skip to skip 3 minutes ahead, because it's just going to be a lot of math to solve this. And it's going to be the same with our next slide. And so the first calculation I want you to do is to look at all of these different concentration units: molarity, molality, percent by mass, mole fraction, and mole percent of ethylene glycol, the major component of antifreeze, that has been dissolved in 0.5 kilograms of water and that you've put into your radiator, and that has a final volume of 515 milliliters. So I'll encourage you to pause the video right now, and the first thing that I recommend you do is just write down all the known values that you have. Okay, so pause the video here. All right, so welcome back. So like I said, the first thing I'll do is I'll write down everything I know. So I have my mass of solute is 17.2 grams, and I'll be able to use that in order to calculate the moles of solute. I know that my mass of solvent, and I shouldn't put SOLN, I should put SOLV for solvent, that's 0.5 kilograms, or 500 grams. And I have a final volume, which in this case just means our solution volume is equal to 515 milliliters. And so, if I'm going to do these in order, I would say, excuse me, that the first one I might want to do is molarity. I know that molarity is defined as moles of solute over volume of solution. And I already have the volume of solution. So I just need to figure out my moles of solute. So the way I'm going to get moles of solute is I'm just going to take that 17.2 grams, that mass of solute, multiply that, or rather divide it by its molecular weight. And in this case, that's 1 mole per 60, I can't read my own writing here. I think that's 62.07 grams. And that would give me a number of moles of 0.2771. So this is that number of moles. And with this, I'm actually able to calculate quite a few different things. So I can then put in everything I know here. So 0.2771 divided by my solution volume of 0.515 liters, converting milliliters to liters. And I'd get that this is 0.538 molar. And I kind of squished that, so let me just scooch it and I'll just put it underneath my molarity. So 0.538 molar. If I want to do molality, I actually have everything I need for molality, because we said molality is just equal to moles solute over kilograms of solvent. I actually have my mass of solvent right here, so I can take my moles, 0.2771 moles, divide by my kilograms of solvent, so 500 kilograms, and I'd get that my molality is 0.554. Give that a little m. And just to show kind of a tick of what we use these things for, I use moles of solute for my molarity. I use moles of solute for my molality. And then I use the mass of solvent for my molality and my solution volume for my molarity. The next one up we want to do is percent by mass. And so we'll find that this one's kind of pretty simple. We have our mass of solute, and in order to get our mass of solution, we're just going to add mass of solute to mass of solvent. So we'd say mass percent is just equal to 17.2 grams divided by 17.2 grams plus 500 grams. And we get that that is, excuse me, we can multiply that by 100 to get a percentage. We get that's 3.3%. The next one up is mole fraction. And so in this case, we're actually having to do one more transformation. We already have our moles of solute, but now we need our moles of solvent. And so the way we're going to get moles of, not sols, but moles, the way we're going to get moles of solvent is we'll take that mass of 500 grams, and we said it was water, so 500 grams H2O. We'll convert that into moles by dividing by its molecular weight of 18 grams per mole. We get that this is 27, not that, but 27.75 moles H2. And we'll put a check mark by this, and we'll say that our mole fraction is just equal to the moles of solute, 0.2771, divided by the total number of moles, so that's 0.2771 plus 27.75. And when we do that calculation, that'll give us 9.89 times 10 to the negative 3. And then finally, in order to get our mole percent, we'll just take that and then we'll multiply it by 100. So our mole percent is just equal to our mole fraction from before times 100%. And we'd get that in this case, that's 0.989% by a molar amount. Okay? And so hopefully those are all the answers you got before. And so this second slide here is just asking you to do a very, very similar set of calculations, but in this case, you're given your initial concentration as 5% by volume, or 5% volume over volume of acetic acid, and we're asking you to calculate each of those different parameters. So once again, write down everything you know, pause the video here, and then we'll come back and solve this together. All right. I assume you've come back from, calculating all this through. So I'm going to write down everything I know. I know that my volume over volume percent of acetic acid is 5%. And that must mean I have 5 milliliters of acetic acid, which I'll put its chemical formula here, CH3COOH, per 100 milliliters of solution. So that's one thing I know. Another thing I know is that I have a density of solution, the density of the vinegar, so that is our solution. So we can say solution is 1.01 grams per mil. And then the density for pure acetic acid is going to be 1.05 grams per mil. So that's everything that we know. And so the easiest way to solve this is eventually we're going to need to assume some amount of a sample volume that we're going to use for molarity. We'll then manipulate that volume to a mass of solvent to get our molality, and then we'll be able to calculate mole fraction and mole percent, just like we did on the previous slide. And so for simplicity, what we can say is that let's say we have a solution volume of 1 liter. And so if we have 1 liter of solution, 1 liter of solution, that's the same as saying we have 1,000 milliliters of solution. We'll multiply that by the density of the solution, 1.01 grams per 1 mil. Cancel out mil, cancel out mil. That means that the total mass of our solution is let me express this in grams, 1,010 grams of solution. And so by doing this assumed volume, what we can do is now what we can take is we can figure out how much, if we have this much mass of solution, if we can figure out how much mass of solute we have, that'll allow us to do our molality. And we also need to figure out, how many moles we have. And so we're actually going to use this 1 liter of solution one more time. So I'm going to use this 1,000 milliliters of solution. I'm going to multiply it in this time. Before I was just getting what's the total mass of the solution. Now I'm going to figure out in the volume over volume calculation, what volume of acetic acid do I have? And so I'm going to multiply this by my volume percentage, which I'll highlight in yellow right now. So I'm going to multiply it. Oh, that was a pen. I wanted to use a highlighter. So let me grab my highlighter now. So I'm going to use this right here and multiply that to a assumed volume of 1 liter. And I'll actually, I'll use green for this. And I'll grab a pen. So I'll multiply this by my volume percentage, which says I have, why is it still yellow? I want green. So I'll multiply this by 5 milliliters of CH3COOH divided by 100 milliliters of solution. Cancel out milliliters of solution, cancel out milliliters of solution, and that says that we'd have 50 milliliters of acetic acid, CH3COOH, and I know using the density of that acetic acid, which I'll now highlight in blue, if I use this, I can figure out, sorry, not that one, highlighting this one. If I use that density, then what I'll be able to do is figure out how much acetic acid I have by mass. So I'm going to multiply this by its density. So that's 1.05 grams per mil for CH3COOH. CH3COOH. I multiply those two together, and I get that that's 52.5 grams acetic acid. I can then, going through, and this is a little bit of a long calculation, I can then divide that by its molecular weight of 60 grams per mole, and I get that 0.875 moles of my acetic acid, and now I am able to calculate a majority of each of these things. So I can do my molarity, which is the number of moles I've calculated, 0.875 moles, dividing by my assumed volume, in this case of 1 liter, and we had to use that to figure out, initially we used a volume of solution to figure out our volume of acetic acid, multiplied that volume of acetic acid by a density to get a mass, divided that mass by the molecular weight. So it's a lot of manipulation, all that depended on this solution volume we assumed. If we had assumed 2 liters, we just have double the number of moles, and we'd get that our molarity here is 0.875 molar. For molality, we just step on down to one of the other things we've calculated. We use our same number of moles, 0.875 moles, and then now we just need a kilograms of solvent. So we're going to take that total mass of solution, subtract out that 52.5 grams of our solute. That gives us that the total mass, excuse me, our total mass there is something like, I think, 1058.5 grams. We divide by, 1058. We divide by 1.0585. That gives us, we have a molality of 0.911. 0.911 molality. And then finally, for our mole fraction, we already have in the numerator our moles of our solute. And so I'll do this with one darker. So we have 0.0875 moles of our solute, and we have 0.875 here. And all we need to do is add the number of moles of water, and we know we have a mass of 1058.5 grams of water. So we take that 1058.5 grams H2O, we divide by the molecular weight of 18 grams per mole, and we'd get that that is around 53.3 moles. And we add that 53.3, we'd get that our mole fraction is 0.0162, which means that our mole percent is just equal to, and I'll do this in one new color, I'll do this in purple, is just going to be multiplying that by 100, so 1.62%. So these are all of the different concentration units we'd have for this problem. And so now that we've done all this, I think at this point, you should feel pretty confident in being able to calculate different concentrations, because we've gone through in practice with calculating, what is each different concentration unit. And now you know how to interconvert between them and utilize, a given percent by mass, a given percent by volume, and go through and do the calculation to figure out every other different type of concentration. So this is everything we'll talk about for concentration, and we'll pick up on Monday by talking a little bit more about what we were finishing with on Wednesday, and then jump into those colligative properties that are very important for our freezing point depression lab.